So in the previous video, we learned the 4-bar mechanisms and the application of Grashoff's criterion. So as I mentioned, for the GATE examination perspective, you just need to remember various categories of the mechanism of the Grashoff's conditions. Grashoff class 1, class 2, class 3, Grashoff, non-Grashoff, special Grashoff, and then what kind of mechanisms you get when you do the convergence of those mechanisms. So that thing you just have to remember, categories from GATE examination. As discussed earlier, the 4-bar chain is quite versatile and it forms the basis of various complicated mechanisms. So that is why the analysis or analytical study of the 4-bar chain is important. As you will be seeing along the lecture that the revolute joints in the 4-bar mechanism can be replaced by other lower pairs and can produce quite complex to analyze mechanisms. But because the basic principles of the 4-bar chain we have understood through the Grashoff's criterion, the same principles can be applied to those mechanisms formed by replacing the lower pair, and we can form a theoretical foundation to do analysis of those complicated mechanisms. Historically speaking, there were various mechanisms available that were developed in the period of 19th and 20th century. So some names were given for different kind of mechanisms. So till now you know the crank, rocker, and rocker mechanism. But since these mechanisms were employed in some particular application, they have different kind of names. So why this is important for us is because in GATE examination sometimes a mechanism name will be given. So we should be able to identify which is the basic, which is the underlying basis of mechanism in that name of the mechanism. Like somebody says a pantograph or a lever or a drag link mechanism, you should be able to relate it to these 3 categories. So there will be name according to function. So according to particular application, there will be name, but you should be able to bring it down to the level of the actual mechanism. Then you will be able to answer the theoretical question. Like the question can be a drag link mechanism falls under which Grashoff's category? So is it Grashoff class 1, or is it non-Grashoff, or special Grashoff, etc. These kind of questions can be found. So a drag link mechanism. So here they have not told in simple words like whether it's a crank rocker or rocker rocker. So you need to remember these kind of names of some typical mechanism which are of historical interest, which are commonly encountered in industry. So we have stated earlier also, and now I'll reiterate. The drag link mechanism is basically a crank or double crank mechanism. So crank or double crank. But the special thing about this double crank is that it's not like a parallelogram double crank that we just discussed towards the end of the last video. In a parallelogram double crank, you get the same circles, same motion is getting transmitted. But in a general double crank, the motion of the two circles may be different. So what will happen here is that one crank will be moving faster, other crank will be moving slower. In a double crank mechanism, it is obviously known that both the circles should be completed in the same time. So the overall duration of circle completion is same for both the links, for both the cranks. But in some instance, at some point of time, one link may be moving faster than the other. Then it will compensate at some other time by being slower. So this is called a drag link mechanism. Here one crank is getting dragged from the other crank. So that's why it's a double crank mechanism. The drag link is a double crank mechanism, and it is not a parallelogram mechanism. So once you know this thing, you can recall your definition of where you normally see the double crank mechanism, which is not a parallelogram. So double crank you see in Grashoff's class 1, where shortest link is fixed. There you get this thing, or you get in special Grashoff mechanism. That special Grashoff means L plus S is equal to P plus Q, which is anti-parallelogram. There you can get the double crank mechanism, where one link is dragging behind the other. So both answers 1 and 3 are correct. So you may have a fourth option like 1 and 3. So that is the correct choice. So like this, you need to remember the names. So the nomenclature of the basic crank rocker mechanisms is as follows. First we have the crank mechanism, or the double crank. In this category we have two subcategories. One is the parallel crank. Here the opposite links are of equal length, they form a parallelogram, and the motion is copied. So two identical circles of equal dimensions, the motion is copied. The other category in this double crank is drag link. Here a parallelogram is not formed, one link moves faster at 10 instants in time, and other instance it moves slow. So the actual time period of rotation is same for both the links in the drag link also, but at a particular instance the speed is different. In the rocker category, different name given to this category is double lever. So if a question comes in exam regarding double lever, you can understand that it's a rocker, and then you can apply the principles, the Grashoff's principle to answer the question. The third category, crank rocker. It is sometimes termed as a crank lever. Following our same line of discussion, we will now cover names of some well-known mechanisms. So this topic is again from the same line of thought, that in the gear be able to identify the mechanism, the basis mechanism, which is inherent in that name. So first we will, in this topic, first we will cover rotary pair mechanisms, and then sliding pairs. The sliding pairs case is more important from the gear perspective, because the slider crank falls under this category. And there are various inversions of this mechanism which are very important from industry perspective, and we get the questions in GATE regularly. So we will go detailed analysis of this mechanism, the sliding pairs. While for the rotary pairs, we will just cover the mechanism name and its formation. We will not go too much into details of the analysis of velocity, acceleration, displacement, all these things. So but we should be aware of the names. So that's why we will cover the revolute joint, rotary joint mechanisms. So the first mechanism in this rotary links category we will cover is a pantograph. Pantograph is a device used to amplify the motion of one point to another. So this is a mechanical amplification. Suppose you know some particular kind of motion of a point, and then you want to amplify it to a larger scale. Then this mechanism is used. Typical applications we can see to create drawings at different scale. So nowadays we all have computer printers, and we have different kind of formatting of documents. We can print a drawing in different scales. But in olden days, if you want to create the same drawing, you want to replicate the same drawing to a larger scale, you can use a pantograph. You can trace the original drawing, and the same drawing will be replicated to a larger scale. That's some other application. So the same principle can be used for tool marking. Suppose you have a drawing to a smaller scale, while the actual job is quite larger in scale. So you can make a tool which can go on the drawing. It can go on the curve on the drawing, and the same curve can be marked on the actual object. So tool marking. Other application is tool guiding, where you have a guiding position where you want to control the position in much larger dimensions, say maybe tens of centimeters, while you want the actual positions to be in mm. So you are controlling in the scale of centimeters, while the actual positioning is happening in the mm scale. So there you can use this mechanism, scaling from larger to smaller, and it is also used in indicators of reciprocating engine. So there the motion of a pressure indicator on top of the engine, that is very small motion, that is translated to larger scale, and it is plotted on the graph to get the crank cycle diagram, P theta diagram. So this is one of the application. So what is the basic mechanism inside a pantograph? I will draw a sketch for you. Basically, it is nothing but a 4-bar chain, parallelogram chain. So you have parallelogram here, A, B, C, D. So AB is equal to CD, and BC is equal to AD. Now in this chain, the link AD is extended and fixed to a rotary link, and the link AB is extended, and we have a particle tracing point called P. So we'll choose some point in the mechanism, say Q here, which is our input point. Q is input point, input motion, and P is the output point. So if you do there is a simple trigonometric calculation and derivation. So if you connect the lines and if you do an analysis, you will find that the small motion of Q is replicated in the same manner, same fashion at P at a different scale. So this scale can be Q motion at Q may be smaller, maybe larger at P, it can be vice versa also. So the motion is replicated to the same scale. You can see the derivation in any standard textbook. Another nomenclature in the mechanisms dictionary is a coupler. A coupler is nothing but a part of mechanism which couples the crank and the rocker. So crank and the rocker in crank rocker arrangement. In crank arrangement, it will connect crank to crank. So coupler couples the crank to crank, crank to rocker, or rocker to rocker. In the mechanisms textbook, you will find application of coupler in a specific manner. But I'll just illustrate that for you here. So this is a standard 4-bar linkage. This is a fixed link which is ground. This is a crank or rocker. This is another crank or rocker, and this is the coupler which connects the crank to the rocker. So coupler, there is a special property of some couplers that a point on the coupler can be used to generate complex curves in its place. Various complex looking curves, complex looking paths can be generated from a point in a coupler, which is called a path generating point. So we'll show some simple examples of this case as we are going forward. So this path generating point is used to create complex curves very accurately from mechanical mechanism. This finds application in motion generating mechanisms. Motion generating mechanisms are used to create accurate We have to pay attention to the word accurate here. Accurate representation of complex graphical motions from relatively simple mechanisms. So as I said here, you should pay attention to this word accurate here. For example, you consider that how do you draw a line, a straight line if you want to draw, how do you draw it? Normally use a ruler, but a line drawn by ruler is as accurate as the ruler's edge is. So if your ruler is not accurate, it may be having some inclination. This is your scale, your ruler. It may be having some serrations, inclination, some curve. Then you cannot get a accurate line. Okay. So so how the question comes here? How was the first ruler created? How was the first accurate straight line was drawn? So for that, you consider the example of a circle. How to create a circle? A circle is normally created with the help of a compass. So you have a compass center point here, and you have a pencil lying down on the other end, or some marker, and you move in a circular fashion. So it gives you a fairly accurate circle curve even for a modest compass, because the distance between the radius, between the center and the periphery will be constant. So even if the mechanism is not so accurately manufactured, it will give you a very fairly accurate circle. So this is a path traced by a mechanism, that is the compass. There is another way to draw a circle, that is to have a pre-manufactured circular object, maybe a coin, and then trace the boundary of the coin to draw a circle. But this is not accurate. So similarly, when you draw a straight line with the help of a ruler, then you are doing something like this. You are trying to draw a circle by tracing a line along the periphery of the coin. So instead of that, you use compass and you get fairly accurate. Similarly, mechanisms can be used to generate desired path accurately. So these are called motion generation mechanisms. We'll cover some categories of straight line motion mechanisms here. So you don't need to study details complete details of these mechanisms, like how these mechanisms are formed and the derivation of how they're tracing a straight line exactly. But you need to know at least the names of them. So sometimes in GATE, if some question comes from the name, you can apply your fundamental knowledge of mechanism. In straight line motion mechanisms, you have two categories. One is exact straight line. So exact straight line mechanisms, and the other category is approximate straight line mechanisms. There are various mechanisms under both the categories. In the straight line mechanisms, you will find Scott Russell's mechanism, you'll find Hart's mechanism, and you'll find Faucher mechanism. In approximate straight line motion, you will find Watt's mechanism, Grashofer mechanism, and Robert mechanism. So I try to give you a high level picture or a snapshot of these mechanisms, but will not go too much in detail. But at least you should know the names. Sometimes a question can come like Hart mechanism is which kind of straight line motion mechanism. So then you can answer that it's an exact straight line mechanism, while a Watt's mechanism is an approximate straight line mechanism. So this kind of simple objective question can be formed from this topic. So the interest in straight line motion mechanism came not only from the perspective of generating accurate straight line curve, but also from perspective of converting rotary motion to translational. I wanted to convert rotary motion to translational and vice versa also. So this is very important in engine. So engine, you get a linear motion of the piston and you want to convert it into rotary motion of the crank shaft, because your wheels will be moving in a rotary fashion, and you want to do it with minimum loss, minimum friction, and light machinery. So as you will be knowing from your studies that a simple mechanism for converting the rotary motion to linear motion is the slider crank mechanism. So in this case, the crank is rotating and you get a linear motion of the piston, or vice versa. The piston is pushed by the hot gases in the engine and it is converting motion to crank. But what happens is here is that due to the rotary movement and the distribution of forces, the force applied at the connecting rod is along the length of the rod. Because of that, you get a linear component of the force on the piston and you get a lateral component of force on the piston. There are two components. We will be studying these forces on the analysis in a slider crank mechanism in much more detail in coming lectures. But I am just giving you a brief idea that there will be a compression in the connecting rod and you will get a lateral thrust. To balance the lateral thrust, you need to have some kind of robust arrangement to take that friction. Because of that normal force, some friction comes, so you have to do some good lubrication and take the lateral thrust. So you want to minimize friction. Because of lateral thrust and friction, there is loss. You want to minimize loss, and to accommodate this lateral thrust, you have to keep bearings, thrust bearings. So your machinery will be complicated. So light machinery. All these three requirements are not met from the slider crank. But so that's why the engineers of 19th century, they want to come up with a different kind of mechanism converting rotary motion to translational. However, there are challenges with those also. So that's why still the slider crank is one of the most widespread used mechanism in industry because of its simplicity. The the straight line mechanisms become very complicated, as you will see in the coming lectures. So that's why they cannot be replicated in the real system. But still, from historical perspective, we should know about those mechanisms.